Hi everyone, welcome back to 3 Deviations. I've got some good news and some bad news for you. The good news is that this is going to be a pretty short video. The bad news is that I don't have much calculus for you today. We're done with trigonometric integrals and we're ready to move on to our next challenge, and that next challenge is called trigonometric substitution. But before we move on to trigonometric substitution, I want to cover some kind of housekeeping things before we move on, because trigonometric substitution is, I think, a beast of an integration technique, and we're going to need to know our trigonometry. I know I've been saying we need to know our trigonometry for those trig integrals, but we really need to know our trigonometry for these trigonometric substitutions and also the Weierstrass substitution, which is going to be coming in a little bit later. So before we dive right into some trig sub, I would like to review some product to sum identities and also some Pythagorean identities. The former will be helpful in your trig integrals, the stuff that we've been covering last time, and the latter will be very helpful in the trigonometric substitutions that we're going to be doing in future videos. Actually, the videos right after this. So let's cover the product to sum identities and the Pythagorean identities. Case 1 for our product to sum identity is that we have the integral of sine of mx times cosine of nx dx. Now, what we do here is we can make the following substitution, and after you do that, you should be pretty good. You get, I'm using these Greek letters, theta and phi. You may have seen theta from a trig course, maybe not phi. You'll see that in multivariable calc. That's an important variable. But for spherical coordinates, but you will see phi again. I like the letter phi and I like saying it, so we're going to use that as a variable here. So we have the sine of theta times the cosine of phi equals 1/2 times the sine of theta minus phi plus the sine of theta plus phi. And of course, I would hope that you remember your identities from trigonometry, your sum and difference identities for the sine and cosine functions, because that will become pertinent fairly soon. Okay, so let's move on to case 2. Case 2 asks, what if we have the integral of sine of mx times the sine of nx dx? So we've got two sine functions, but different arguments. So what we do here is we can use the product to sum identity again, but we say that the sine of theta times the sine of phi is equal to 1/2 times the cosine of theta minus phi minus cosine of theta plus phi. So that is for our second case, and again, these are fairly important if you remember the cosine identities. So the cosine of theta, so if I have cosine of theta plus or minus phi, that's equal to cosine of theta cosine of phi minus plus sine theta sine phi, not theta. It's kind of the opposite. Okay, then we've got the sine of theta plus or minus phi is equal to sine theta cos phi plus or minus sine of phi cosine of theta. Okay, now we can talk about the third case, which is if we have the cosine of mx times the cosine of nx as the integrand. So if you have that as the integrand, what we do is we can use this product to sum identity. Cosine theta cosine phi is equal to 1/2 cosine of theta minus phi plus cosine of theta plus phi. As I just wrote all of those identities out, you should be able to remember that, and this should be something that you can evaluate using an integral of some sort. Okay, so now what we can do is we can review the Pythagorean identities. Now, these are going to become extremely important in our trig sub videos, which we're going to be talking about next. So trig sub is basically when we turn a radical function into a series of trigonometric functions, and we can use triangles and stuff like that in this Pythagorean identity stuff to fix that. So here we have our Pythagorean identities. First off, this one that everybody should remember. This is basically, so we have sine of theta plus, or sine squared theta plus cosine squared theta equals 1. If you imagine your unit circle and you think of your x-axis and your y-axis, you have your hypotenuse here, and your sine of theta is by definition, your height there, if this is 1, and then your cosine theta is by definition your x. That's sine of theta. Okay, now these are a little bit harder to prove geometrically, but you get the tangent squared of theta plus 1 equals the secant squared of theta, and you also get the cotangent squared of theta plus 1 equals the cosecant squared of theta. Okay, so those are the Pythagorean identities. I would hope that you remember these for the next video. We are going to be concerning ourselves with these two mostly. This one will become important, but as you remember how we kind of didn't talk about the cotangent and the cosecant because of how similar it was to the tangent and secant, we're going to be spending a lot more time talking about tangent, secant, and sine and cosine, more so than the cotangent and the cosecant. Well, specifically, we'll be talking about sine, tangent, and